Hello everyone, welcome to this new course Fluid Mechanics, and this is the introductory lecture. So here we'll discuss about the basic definition of fluid, and along with that we'll also discuss the property of fluid, which is called viscosity. And the reason we are only studying the property viscosity along with definition of fluid is because definition itself is intertwined with the property viscosity. Now we can remember that we learned different definitions of fluid. For example, some material or substance, or more precisely a state of matter which does not have its own shape and form, but it takes the shape of the container where it is put. So that kind of a substance is called a fluid. Now there can be some other definitions also. For example, any material which can flow, or coming to the engineering or scientific definition of fluid, it is a matter or state of matter which cannot resist any shear stress. And to be more precise about this whole thing, actually the final definition should be somewhat like material, substance, or a state of matter which deforms continuously under a constant given shear stress. So we'll try to understand what this whole definition means. So we have already learned what are shear stresses and strains. So let's start from the example of a solid rather than a fluid. So imagine a rectangular block like this. Imagine this is to be made of rubber. And when we apply some force here, which is a shear force, and that divided by the area will be shear stress, then this whole thing will be deformed and it will take a different shape, which will be somewhat like this. So this is the deformation, and if we keep on increasing this shear force, then it will keep on deforming more and more. So that's what happens with a solid. However, if you imagine a liquid, suppose some liquid layer is over a surface, and this surface is slightly sloped. That means it has a certain inclination with the horizontal, suppose theta, and in that case the fluid will flow in this direction, and that's because we have a certain shear force which is in this direction, which is the component of gravity. Otherwise, if you take this kind of an element, so if the slope was horizontal, if this floor was horizontal, then the component of gravity in this direction would be 0. But since the floor is slightly sloped, therefore the same element is slightly inclined, and there is a component of gravity along the slope of the floor. So therefore that will act as the shear force, and because of that shear force the fluid will start moving in this direction. So that's what it means, that liquid or fluid will move under shear stress. Now if we go back to the previous definition, that is a state of matter which cannot resist any shear stress, or a state of matter which deforms continuously under a constant shear stress. So now coming back here, if you look at the solid, if we put a certain value of shear stress, then it will deform to a certain angle. Suppose this is theta or phi, whatever you want to call it. Let's say phi 1. If we increase the shear stress, then it will be deforming by a greater angle phi 2 and so on. But in case of a fluid here, even if the shear stress is not increased, we are only putting a constant amount of shear stress. That means the slope of the floor is fixed. That means it is not getting any change in inclination. Even then also, this element, first suppose it was like this, then after some time it will take this kind of shape. Then although the shear stress is remaining same, it will continue to deform like this. And that's what flow means. When it continuously deforms without any increase in the shear stress, then we say that the material is flowing. However, in case of solid, it is only deformation. But in this case, in case of a fluid, it is continuous deformation, and we call that flow. So let's try to understand this in a mathematical way. So the angular deformation under any shear stress will be called shear strain. But in case of fluid, as we have seen, the shear strain itself will not remain constant. The strain will keep on increasing even if we do not increase the stress, even if we put a constant stress. So in that case, instead of measuring the shear strain itself, we'll measure something else, which is the rate of shear strain or rate of deformation. So, and that will be given as d theta by dt. That is, if we have a fluid element like this, after some time it will be deforming by this angle, suppose theta, and if it takes dt amount of time to change this deformation further by an amount d theta, which is this much or this much, then d theta by dt is called the rate of shear strain, or rate of angular deformation. Now, just like in case of solids, different solids will deform by a different angle under different shear stresses. In case of fluids also, they will deform at different rates under the same shear stress. So if the rate of deformation is less, that means under a given shear stress, a fluid or a liquid is moving at a slower rate or deforming at a slower rate, then it is said to have more viscosity, or to be said a viscous fluid. On the other hand, if it moves or it deforms quite rapidly under the same shear stress, in that case it is called a less viscous fluid, or a fluid with a smaller value of viscosity. Now, in some situations, we also use a term called ideal fluid. That means a fluid with no viscosity. In reality, all fluids will have some viscosity, but in some situations, all the other forces that govern the flow of fluid are so dominant that viscosity becomes almost insignificant, and therefore, in those situations, just to remove one of the mathematical parameters, we assume that the viscosity is of no importance. Generally, that happens in case of large-scale flow phenomenon. For example, flow in oceans, flow in rivers, etc. So in that case, all the other forces are so dominant that viscosity becomes almost irrelevant, and there we assume the flow to be an ideal fluid. Assume the fluid to be an ideal fluid. So in reality, no fluid is actually ideal. Any real fluid will always have some amount of viscosity, no matter how small. Now, as we have discussed how it will behave, if the fluid has a smaller viscosity, then under a very small shear stress, it will have a very large deformation or rate of deformation. So therefore, this kind of a graph may be used to show the relationship between the shear stress and rate of shear strain or rate of angular deformation. If the fluid has a high viscosity, in that case, the slope will be steeper, and for very highly viscous fluids, it will be even steeper. For an ideal fluid, the relation between shear stress and rate of shear strain will be this horizontal line parallel to the x-axis. Now, let's discuss this viscosity in detail. So as we have seen, as shear stress increases, rate of deformation also increases. That means tau, which is the shear stress, is proportional or directly proportional to d theta by dt, which is the rate of deformation. Now the next stage in this kind of a relationship is to introduce a constant of proportionality. So if we want to make this relationship an equation rather than just a proportionality relationship, then we'll have to introduce this term mu, that is tau equals to some coefficient multiplied by d theta by dt. Now this constant of proportionality mu, which can also be defined as the ratio of shear stress and rate of deformation, is called the coefficient of viscosity or dynamic viscosity. So as we have discussed, different fluids will have different relationship between shear stress and rate of deformation or rate of shear strain. So the coefficient of viscosity mu, which is equal to the shear stress divided by d theta by dt, it will be basically the slope of these relationship curves between stress and rate of strain. So this is tau and this is d theta by dt, and tau divided by d theta by dt is the slope of this line, and therefore, as we have learned in the previous slide also, the slope of this line will represent the coefficient of viscosity. The bigger the slope, bigger the viscosity. For example, for this curve, tau is greater and d theta by dt is smaller, and therefore mu will be greater. And for this curve, tau is smaller, d theta by dt is greater, and therefore mu will be smaller. And for ideal fluid, tau is 0. For any deformation, the shear stress is not even required. So in that case, it will be this horizontal line. Now let's try to compare this whole thing with what we have already learned in solid mechanics. That is, for solids, shear stress is proportional to shear strain that we know, that is tau is proportional to theta. And making it an equation, we got that tau is equal to G, which is the modulus of rigidity, multiplied by the shear strain, which is theta, and therefore the modulus of rigidity is tau by theta, or shear stress by shear strain. On the other hand, in case of fluid, relationship is quite similar, but this additional time parameters will appear because we are not dealing with strain only, but we are dealing with rate of strain, and therefore you can see the similarity. Here it is tau is proportional to strain, here it is proportional to rate of strain, and here tau equals some constant multiplied by strain, here it is some constant multiplied by rate of strain, and this constant in case of solids it is called modulus of rigidity, in case of fluids it is called the coefficient of viscosity, and it is again given by, here it is the ratio of stress by strain, here it is the ratio of stress by rate of strain. So the relationship will be similar here. For example, if this is rubber having a low modulus of rigidity, that means it will deform easily under a given stress. On the other hand, suppose this is steel, which will be deforming very less under a given stress, and it will deform under a very high value of shear stress. Similarly, here, suppose this is a very thin liquid or thin fluid. By the word thin, we mean something which flows very easily. For example, spirit or some petroleum products like petrol, etc. Then comes water, which is slightly more viscous, and then comes some viscous fluids such as lubricant oils, then honey, ketchup, and all those kind of fluids. And gas will be having very low viscosity, very close to this horizontal line, most of the gases. So now we have a good comparison between the solid and liquid behavior or fluid behavior. Now let's try to go into something called the Newton's law of viscosity. We have already learned this Newton's law of viscosity, although we did not name it as such. So the statement of this law is that rate of change of shear strain or rate of deformation or shear rate, whatever you want to call it, of a fluid is directly proportional to the applied shear stress. So this we have already learned. Now this itself is called the Newton's law of viscosity, and from that we found the definition of this coefficient of viscosity. And any fluid that obeys this law is called a Newtonian fluid. When we classify something as Newtonian fluid, that means there are some fluids which will not obey this law, and those fluids are called non-Newtonian fluids. So we'll learn how they will behave. So for Newtonian fluids, shear stress is linearly related to the shear strain rate. That means if we put a graph between shear stress and shear strain, then it will be a linear graph, a straight line, and the slope is constant, which is equal to mu, the coefficient of viscosity. But for some fluids, the relationship may not be linear. That means instead of a straight line, it can be like this, or it may be like this. It can be curved in both ways, concave upward or concave downward. So shear stress may be proportional to some exponential of deformation rate. So instead of being proportional to d theta by dt itself, it may be proportional to d theta by dt to the power n, where n is not equal to 1. When n is equal to 1, then definitely it is a Newtonian fluid. If it is not equal to 1, in that case we call it a non-Newtonian fluid. One thing we have to remember that n is always greater than 0. It cannot be negative. That means if shear stress increases, the shear strain or the strain rate cannot decrease. It will always increase, but the rate of increase will be somewhat different. It may not be constant always, it may be somewhat else. So we'll see how that turns out. So this is the equation. Tau is proportional to some power of d theta by dt. For Newtonian fluids, it is this n is equal to 1. For non-Newtonian fluids, they are not equal to 1, and if it is not equal to 1, there are different options. One is when it is less than 1, and another one is when it is greater than 1. Now, what do they both mean? So, when n is less than 1, for reference, let's draw this this Newtonian fluid curve where it is a linear relationship, tau and d theta by dt. If n is less than 1, then what will happen is as shear stress increases, for lower value of shear stresses, the strain rate will be greater, but as stress increases, the strain will increase at a greater rate. In case of a Newtonian fluid, it increased at a constant rate, but in case of this kind of non-Newtonian fluid where n is less than 1, the shear strain rate will be increasing at a greater rate. And physically what it means is that when we have such a fluid, when we apply some small amount of shear stress, it will appear that the fluid is quite viscous. But if we try to apply a very high stress, if you want to move it at a if we apply greater shear stress, then it will behave as a fluid having low viscosity. And that's because from the curve itself it is apparent that the slope of the curve, which is the viscosity, as we have learned in the previous slides, it will decrease as stress increases. So that means at this point the viscosity will be higher, but as we increase the stress somewhere around here, the slope is lower and therefore the viscosity will appear to be lower. On the other hand, if n is greater than 1, in that case it will be the reverse of this. Under low stress, the liquid or the fluid will behave as a very low viscosity fluid. The viscosity will appear to be smaller, but as we increase the stress, it will appear more and more viscous. So that kind of fluid is called a dilatant, and this kind of fluid where it is the shear strain rate increases or the viscosity decreases with application of shear stress is called pseudoplastic, and the type of fluid where viscosity increases with greater application of shear stress is called a dilatant. These are also called shear thickening fluids. That means once you apply shear stress, more shear stress, the liquid appears to be thicker. On the other hand, in this type of fluid, as you apply more shear, the fluid becomes thin or less viscous or more easier to flow. So these are called shear thinning liquids or shear thinning fluids, and these are called shear thickening fluids. So examples you can see for pseudoplastics, it is blood, acrylic paints, quicksand, etc. And on the other hand, dilatant will be cornstarch, some particular ratio of sand and water mixtures. This quicksand also is a sand and water mixture, but at a different ratio. So this sand and water mixture at different ratios will behave differently. At some ratio, it will behave as shear thinning liquid, and at some ratio, it will behave as shear thickening liquid. Then there is another type of fluid which is called Bingham plastic. In Bingham plastic, the property is that the relationship is linear because there is no power, or the power is equal to 1, but there is some addition to this relationship, that is tau c. That means although the curve will be a straight line like this, then it will always have some minimum shear stress tau c, beyond which only it will start behaving like a liquid or a fluid. Below that shear stress, it will keep behaving like a solid. So this kind of fluid is called a Bingham plastic. Here we have to also multiply the term mu. So this is, for example, your toothpaste will appear like that when you put that toothpaste on top of the brush, top of your toothbrush, then it will stay like that as if it is a solid. But the moment you apply some force, it will start some shear stress, it will start flowing like a liquid, although a very viscous liquid, but still liquid nonetheless. So these are different types of non-Newtonian fluids. You can look for different examples, and sometimes you can also do some experiments using different household items. For example, you can mix cornstarch with half the amount of water, and then it will behave as a dilatant, where if you want to stir it with a spoon, if you do it slowly, you can easily do it, but once you try to do it very fast, that means you apply very large shear force or shear stress, then it becomes very difficult and it almost behaves like a solid. And sometimes if you get the proportion right, it will appear as if you try to punch the surface of this cornstarch mixture, then it will give you resistance like a solid surface. However, if you simply want to dip your hand inside slowly, then it will be like a very smooth or viscous liquid. So you can do that experiment at your home. Cornstarch is easy to find. Then there are some other types of non-Newtonian fluids. One is a rheopactic fluid, where viscosity increases with time. That means even if we put a constant shear stress, means the shear stress is not increased, but if we keep applying the shear stress for a long time, the viscosity increases and the fluid behaves as more viscous, and in some cases almost like a semi-solid. On the other hand, the reverse is the case of thixotropic fluids, where viscosity decreases with time and a constant shear stress is applied. So they are sometimes confused with dilatants and pseudoplastics, but in dilatants and pseudoplastics, the change in viscosity is because of change in shear stress, the value of shear stress. But in this case, the same shear stress, if applied for certain amount of time, with time the viscosity will either increase or decrease. Although these kind of fluids are not very common, but they do have very important engineering applications. Now let's try to go into a different topic, which is called the velocity gradient. It is whatever we have learned as d theta by dt, that is the rate of shear deformation. Sometimes it is also called the velocity gradient, and we'll see why that is the case. So by velocity gradient, by definition, it is the difference in velocity between two layers of fluid separated by a unit dimension perpendicular to the flow direction. That means if a fluid element is flowing like this, suppose this is the rectangular fluid element, when it is flowing at some point of time it will become like this, then it will take this shape, then it will take this shape, then it will take this shape, and that's what flowing means. Now when it is happening, we can understand that different layers of the fluid is moving at different velocity, because if this was the original element, when it is assuming this shape, when it is taking this shape after a certain time, suppose, that means this particle is moving at a slower velocity than this particle. Obviously these particles are moving at a higher velocity than particles below them, and so on. Okay, and this particle which is in contact with the floor or the boundary or the solid boundary is not moving at all. So if we find out this difference in velocity and divide it by this distance, then that is called the velocity gradient. That means the change in velocity or the difference in velocity per unit distance measured perpendicular to the direction of flow. So this is the flow direction, and in a direction perpendicular to that, what is the difference in velocity? That means this layer is flowing at a different velocity, this is flowing at a different velocity, and so on. Now we'll try to prove that that is the same as the rate of deformation. So du by dy by definition is the velocity gradient, which is du, it is the change in velocity or the difference in velocity and dy is the distance across or perpendicular to the direction of velocity. So rate of change of shear strain or rate of deformation or shear rate, we'll see how that is the same thing. So d theta by dt, again if we take this kind of an element, suppose this is the angle by which it deformed over a given time dt. So d theta by dt will be equal to dx by dy, where this is dx, the distance by which the top layer of the element has deformed, and dy is this distance, the perpendicular distance, and dx by dy for a small value of this, for a small value of deformation, it will be almost equal to the angle itself. Otherwise it is actually tan of the angle. Dx by dy is equal to tan of d theta. However, for a small value of d theta, it is almost equal to d theta. And therefore, dx by dy is d theta, then divided by dt, and then we can say that dx by dt is the velocity, and after that dx by dt is divided by dy will give us du by dy, and therefore we can say that the Newton's law of viscosity itself can be written as tau equals mu into du by dy, which is the same as d theta by dt. So we have learned how viscosity is related to shear stress and shear strain. So if we want to find a definition of viscosity, then we can say that it is the property of fluid by which it will resist relative motion between adjacent layers. Means if we consider this element which is deforming like this, then we can say that if it is composed of different layers like this, then all these layers are moving at different velocities. If we make this very small layers, suppose, and viscosity is the property by which it will resist the relative motion between adjacent layers. And by relative motion, I mean if this is moving at a velocity v1 and this is moving at a velocity v2, then v1 minus v2 is the relative velocity or relative motion between this layer and this layer. And if viscosity increases, then instead of deforming like this, it will deform only by this amount. And a very low viscosity fluid will move at a very high rate like this. That means the relative velocity is very high here. So if viscosity increases, the relative velocity or the relative motion will be reduced, and if viscosity is low, then the relative motion will be increased under a given constant shear stress. So this is the definition of viscosity, and now let's go to the factors affecting viscosity. This is not something that we are not very concerned with, but still it is important to have some idea of what affects the viscosity. Intermolecular forces of attraction definitely will increase viscosity, because if the particles are tied together with one another, then it will be very difficult to move them relatively, very difficult to create relative motion between two particles. Suppose these particles are very strongly bonded molecules of fluid, then if this moves, this will also move. If the bond is weaker, then if this moves, then this can move, but its movement will not affect this particle as much. That means the relative velocity is possible. Higher relative velocity is possible. Then molecular structure and composition of fluid will also affect viscosity. Generally, fluids which have larger molecules like some polymers, petroleum products will generally have higher viscosity, and simpler fluids having slower molecular structures and pure fluids, they will be generally having lower viscosity. And composition of fluid means if it is some kind of solution or colloid, etc., or gel, in that case they will generally behave as viscous fluids. Temperature will also affect the viscosity, as if temperature increases, generally the intermolecular forces decrease, and therefore the velocity also decrease, although there are very few examples where increase in temperature will actually increase the viscosity. Then stress, as we have already learned in case of non-Newtonian fluids, and time, similarly they will affect non-Newtonian fluids. Now when we talk about fluids, we have two different types of fluids, basically liquids and gases. So in case of liquids, this temperature, as temperature increases, velocity will decrease. On the other hand, in case of gas, as temperature increases, well, viscosity will also increase. So this is something to remember. However, in most of our civil engineering applications, we will not be dealing most with motion of gases or viscosity of gases. So for most of the fluids, for most of the liquids, as temperature increases, viscosity decreases. Then, so we have learned how viscosity is important in fluid studies. Now let's revisit the definitions that we presented at the beginning. So material or substance or state of matter which does not have its own shape or form but assumes the shape of the container it is put in, so that is fluid, or the definition of fluid. But it is not applicable if we do not have gravity. If we have a glass of water, if we have a glass and try to put water in it under a gravitational field when we are on Earth, then it will take the shape of the glass. But if we are in space, then it may not take the shape of the glass and water may simply float around. So it will not be a proper definition or universal definition. Then a material which can flow, but that is a good definition. However, for that we'll have to define what is flow. What kind of motion do we call flow? If a particle is moving, that cannot be said flow. It's just motion or velocity, translation and motion. However, if these different particles keep moving under a given shear stress, then it is called flow. However, this kind of flow-like behavior can also be seen in case of granular materials such as sand and gravels when they slide over a hill slope during landslides, etc. So therefore, for some times, some brief moments, those solids can also behave as if they are flowing. Therefore, this definition is also not very appropriate or not universal. Then the other definition is material which cannot resist any shear stress. So that is a good example. No matter how small the stress is, if it is a fluid, it will start flowing. However, that is not the case in case of, one exception is that the Bingham plastic, as we discussed, it will start flowing only after a certain value of shear stress. So beyond that it will behave as a fluid, but up to that much shear stress it will behave as a solid. So therefore, instead of writing the definition like this, we can converge on this definition, which is material, substance or state of matter which deforms continuously under a constant shear stress. So Doesn't matter if it starts here or here, if there is a constant shear stress which moves it, then there is a constant rate of deformation. That means it will keep deforming at this particular rate. If we increase the shear stress, definitely it will deform at a higher rate. But even if we do not increase the shear stress, it will keep deforming at a given rate, which is true for almost all the fluids. So that is something that we can accept as an engineering or scientific definition of fluid. So this is our introductory lecture about fluid mechanics, and we'll dive into the different properties of fluids in our subsequent lectures. Thank you.